Japan and New Zealand have brought a Japanese-designed frigate to the front of Wellington's future fleet debate after a round of senior-level talks in Tokyo on October 20, 2025. Rear Admiral Garen Golding, the head of the Royal New Zealand Navy, met Japan's Defense Minister, Gen Nakatani, for detailed discussions on a modernized version of the Mogami-class, often referred to as the new FFM configuration. While the meeting produced no contract announcement, officials on both sides framed the dialogue as a serious technical and industrial evaluation rather than a cursory courtesy call, indicating the design has moved into genuine contention for New Zealand's next frigate program in the mid-2030s. Momentum for the Japanese option has been buoyed by developments across the Tasman Sea. On August 5, 2025, Australia selected an enlarged derivative of the Mogami as the baseline for its General Purpose Frigate program. Canberra's plan envisages 11 ships, with the first 3 to be constructed by Mitsubishi Heavy Industries in Japan for deliveries around 2029 to 2030, followed by a shift to local assembly at Henderson in Western Australia. That two-site production blueprint offers a ready model for a smaller neighbor: start with early hulls from a mature line to meet capability gaps sooner, then integrate domestic industry where it adds cost-effective value. New Zealand's timing problem is as much about people as it is about steel. The RNZN's 2 Anzac-class frigates, HMNZS Te Kaha and HMNZS Te Mana, received major combat systems upgrades to extend their utility toward the mid-2030s, yet those improvements cannot fully offset the rising maintenance burden of aging hulls. Persistent crew shortages have further constrained readiness, with official figures in recent years pointing to hundreds of vacancies across the service. In that environment, a successor platform that achieves more with fewer sailors is not a luxury, it is a prerequisite for maintaining presence in one of the world's largest exclusive economic zones and contributing credibly to coalition task groups. The Mogami family was developed by Japan to replace the Asagiri and Abukuma classes with a compact, heavily automated, multi-mission surface combatant. The baseline ship measures roughly 133 meters with a full load displacement near 5,500 tons and typically sails with a crew of about 90. A combined diesel and gas propulsion system supports 30-plus knot sprints and long-range transits. A distinctive feature is its integrated combat information center, which consolidates navigation, platform management, and tactical functions around panoramic, data-rich displays to shrink manning without sacrificing situational awareness. The architecture is deliberately modular, enabling shifts between warfare areas without wholesale redesign. Weapons and sensors on the class aim to deliver credible punch in a lean form factor. A 127mm main gun anchors the forward deck, backed by a baseline fit of 16 Mk-41 vertical launch cells that can host surface-to-air and anti-submarine weapons. Anti-ship firepower traditionally comes from 8 canistered missiles, while twin 324mm torpedo triplets provide a lightweight ASW option. An active electronically scanned array radar, variable depth sonar, and a towed array give the frigate an ASW profile that belies its size, and attention to topside shaping and machinery quieting reduces signatures across radar, infrared, and acoustic bands. Organic aviation through an SH-60 series helicopter and the ability to deploy unmanned surface and underwater vehicles extend the ship's reach for surveillance, mine countermeasures, and submarine prosecution. The new FFM configuration that has captured attention in both Canberra and Wellington expands this baseline. The hull is stretched to roughly 142 meters with a beam near 17 meters and displacement around 6,200 tons. Vertical launch capacity doubles to 32 Mk-41 cells, opening room for layered air defense and deeper ASW magazines, and, subject to export policy, the potential integration of longer-range interceptors or strike effects. Upgraded sensors and an expanded electronic warfare suite aim for better detection and resilience in a dense electromagnetic environment, while an evolved combat center overlays augmented reality and decision aids to keep crew numbers low as complexity rises. Engineers have also built in power and space margins to host future systems such as higher power radars, directed energy weapons, and more capable unmanned vehicles. For New Zealand, the appeal is not merely technical. Australia's adoption of a closely related design promises economies of scale that a two-ship national buy could never achieve on its own. Shared components, training devices, software baselines, and maintenance infrastructure reduce lifetime costs and lower risk. The prospect of synchronized training pipelines and interchangeable spares across Anzac partners would compress logistics tails for deployments and simplify surge operations. In a region where distance multiplies every cost, such commonality can be as decisive as any headline specification. Industrial strategy will shape the decision just as much as performance metrics. New Zealand has historically favored pragmatic approaches that deliver capability while preserving budget headroom and creating targeted local work. A phased procurement, early hulls produced abroad to accelerate delivery, followed by structured domestic participation in integration, testing, or through-life support, would mirror Australia's hybrid model without overpromising on the scale of national shipyard capacity. That approach supports the workforce with steady, specialized roles and builds sovereign sustainment expertise where it matters most: software maintenance, systems integration, and lifecycle upgrades. Strategically, a shift toward Japanese-designed frigates would align with Wellington's increasing emphasis on a free and open Indo-Pacific, a theme echoed during high-level visits and exercises with regional partners. Closer cooperation with Tokyo, dovetailing with enduring links to Australia and the United States, would embed the RNZN in a network of navies operating similar platforms, facilitating combined training, information sharing, and rapid adaptation to emerging threats. Interoperability would not be an afterthought bolted on via radios and data links. It would be engineered into the ships from the outset through common sensors, weapons interfaces, and tactics. None of this eliminates competition. New Zealand will inevitably weigh alternatives against price, delivery timelines, risk, and sovereignty concerns, and will test how each candidate performs in the Southern Ocean's harsh seas and in the constabulary missions that occupy much of the RNZN schedule. Yet the Tokyo consultations, coupled with Australia's August choice, have granted the new FFM a credibility that many paper proposals lack. It is a variant of a platform already at sea with the Japan Maritime Self-Defense Force, backed by a shipbuilder whose production lines and supply chains are active today rather than theoretical. In the months ahead, the conversation is likely to move from concept framing to harder questions about cost profiles, manning models, and through-life support. How many sailors can the RNZN sustainably field for a ship of this size, and what automation and training solutions would be required to meet that target? Which weapons and sensors offer the best balance between capability and affordability for New Zealand's mission set, from high-end warfare to disaster relief and maritime security? And what division of labor between foreign shipyards and New Zealand industry would deliver the first hulls quickly without creating long-term sustainment gaps? The answers will determine whether the new FFM's combination of scale, automation, and regional commonality becomes the backbone of New Zealand's blue water future, or remains a compelling benchmark that drives the final choice toward a different, but similarly optimized, path.